This review is for people who already know how to program in C. If you haven't used C for very long, or not used it in a while, this should help you get up to speed. After completing the review, you should be comfortable writing programs in C. Follow along with all the activities to get the most out of the review. If you haven't already done so, go through the C tools video. The printf function, found in the standard.io.h header file, is used to display formatted output. Printf uses conversion specifiers, indicated with the % character, to print out the appropriate values. A conversion specifier tells printf how to interpret the variable. For example, to print out an int, use %d. If you want to print out an int as octal, use %o. Specify hexadecimal with %x. A lowercase x prints the hex letters as lowercase, while an uppercase x prints them as uppercase. To force a number to be printed as 2 hex digits, use %02x. The 0 tells printf to use a 0 if the value is only 1 digit, and the 2 says to print out 2 digits. The compiler issues a warning if you pass the wrong type for the conversion specifier and have the appropriate compiler warning set. Constants are an important part of programming. Rather than hardcode values, a constant gives a value a name. It's important to name things. Variables get names to make their purpose clear. Functions have names that describe what the lines of code inside of them do. Constants get names so programmers understand their purpose. Constants also make it easy to change the value. Imagine you have some code like this. What does the 60 represent? Is it seconds, minutes, or something else? It would help if the x and y variables had meaningful names. You can use refactor rename to have CLion intelligently change all the uses of the variable to the new name. Prices assigned tasks times 60 makes understanding what is going on easier. You could add a comment to explain what 60 is. There is a saying, don't comment bad code, rewrite it. To define a constant in C, use the number define preprocessor directive. The preprocessor replaces cost per task with 60 everywhere it appears. The new code is much easier to understand than the original, and if the cost per task changes, you only have to change the number define and all the code is updated. An enumerated type, or enum, is a special type of constant. An enum is a set of named int values. By default, enums start at 0. You can assign a specific value to an enum, and the numbering continues from there. Enums can be better than a plain int because the value has a name, which makes the code easier to understand. Enums are essentially types, like bool, int, or char, and the compiler can tell if they're being used properly. C is a low-level language. Some people have referred to it as a portable assembly language. A low-level language exposes parts of the underlying hardware and places very few restrictions on the platform. This lack of restrictions is most noticeable when declaring variables. The C standard says things like a short is at least 16 bits and an int is at least as big as a short. Contrast this to a platform like Java, where an int is always 32 bits, no matter the underlying hardware or operating system. If you want to write programs that are portable to multiple platforms, you must limit the types you use. The C standard guarantees that a char variable is at least 8 bits. POSIX requires a char to be exactly 8 bits. Rather than use int, which has a platform-specific size, the standard int.h header file provides a set of integer types with well-defined sizes. Int 8t is exactly 8 bits. Int 16t is exactly 16 bits. Int 32t is exactly 32 bits. And int 64t is exactly 64 bits. POSIX requires that the 8, 16, and 32 types exist. These types are signed, meaning that they can have positive or negative values. Unsigned versions start with a U, for example, uint32t. An unsigned integer can only have values greater than or equal to 0. Printf requires special conversion specifiers for these values. These specifiers are found in the int_types.h header file. There are also constants for the smallest and largest value for each type. Size t, defined in the standard def.h header file, is an unsigned integer type. Size t is large enough to refer to the largest possible array on the platform. In practical terms, size t can hold a memory address, though, strictly speaking, depending on the platform, that may not be true. Welcome to the wonderful world of vagaries of C types. Many standard C functions use size t. Use the %zu conversion specifier for size t. Size max is the largest value that a variable of type size t can hold. The smallest allowable value for size max is 65,535, meaning that size t must be at least 16 bits. The standard bool.h header file provides the bool type. A bool must be at least large enough to hold a 0 for false and a 1 for true. Generally, in C, true is any value other than 0. Use the %d conversion specifier, same as int. If you assign a bool any other value than 0, false, or 1, true, it will become 1. Use the char bit constant to see how many bits are in a char. If you're on a POSIX system, it must be 8. If you're on a non-POSIX system, it is still probably 8. Use sizeof to determine the size in bytes of each type. The number of bytes for size t and bool may differ on your system. Any data to be shared between platforms must be declared as int_nt or uint_nt. Chars are also shareable between POSIX systems. Float and double are floating point types. The C standard places very few requirements on floating point values, so using them in portable programs is not a good idea unless an API requires their use. Using only specific sized integer types to share data may seem very limiting. In a computer, all values are a series of zeros and ones, which means you can express any value with these types. For example, instead of using floating point to represent dollars and cents, express currency in cents only. It is important to note that C does not require that memory be initialized. If you declare a variable and use it without giving it a value, it will have a random value. Depending on the platform, the bits may all be set to 0, but do not depend on that. Remember that, in a computer, everything is represented by bits. A uint8t is an unsigned 8-bit integer. You can view that as octal, decimal, or hexadecimal. The value doesn't change, just the presentation. There's no built-in way in standard C or POSIX to display a value in binary. First, create a prototype to print a uint8t value as bits. Print binary will need a way to print each bit of the uint8t. Create a prototype for that function too. There are a few ways to get a bit out of a variable. One way is to shift the bit to the rightmost position and then extract the bit by ANDing it. If 0 and 1 are ANDed, the result is 0. If 1 and 1 are ANDed, the result is 1. Let's look at how that works for the number 13. 13 is binary 1101. Right shifting by 0 doesn't change the value. ANDing with 1 gives 1. Right shifting by 1 moves every bit to the right by 1. The rightmost bit is lost. The leftmost bit becomes 0. ANDing 0 with 1 gives 0. Right shifting by 2 moves every bit to the right by 2. The two rightmost bits are lost. The two leftmost bits become 0. ANDing 1 with 1 gives 1. Right shifting by 3 moves every bit to the right by 3. ANDing 1 with 1 gives 1. The rest of the bits will all be 0. The getBit function takes in the value and the position. Translate the position by the amount to shift by. Bit position 0 has to shift 7 times. Bit position 7 has to shift 0 times. Shift the value by the required amount. AND with 1 to get the bit value. Putting this code into a function gives it a name. The function does one very well-defined task: get a bit at a particular position. It's easy to understand this code, and it's easy to test this code. Now write the print binary function. There have to be 8 variables, 1 for each bit. Get the value for each bit. If you think this is ugly, yes it is. It's important to make code that works and is easy to understand. You can improve it later if you want to. Putting things into functions makes it easier when you want to make the code better later on. You notice that I separate variable declarations from variable assignments. This isn't required, but my reason for it is that I value consistency. Since not all variables can have values when declared, I choose to give no variable a value when declared. When I learned C, variables had to be declared at the beginning of a block. C no longer has this restriction, but I choose to use it because putting the variables at the top of the block makes it easier to find them. Once you have all the bits, print them. Test the function with a few values. Try to pick ones at the edge cases. Zero, 1, 254, and 255 are all at or near the upper and lower bounds, making them ideal test cases. 85 is close to the middle, making it a good test case too. Run the program and make sure the output is what you expect. Since we've already seen how 13 works on paper, we can debug it and verify that it matches step by step. Set a breakpoint on print binary 13. Run the debugger. Using the debugger to trace code is an excellent way to see what is happening in the running program. Step into the print binary function. Step over until you get to the assignment for bit 4. Stepping over the function call runs the function, you just don't see it happen line by line as you do with single stepping. Step into the getBit function. The value is 13. Step. Shifted by is 3. One ANDed with 1 is 1. Step 2 more times to leave the function. Step into getBit for bit 5. Set a breakpoint on the return. Select Resume Program. All of the code between the start of the function and the return has run. You can see the values of the variables. Stepping out leaves the function, still executing all the code. Step into getBit for bit 6. Right mouse click on the return. Select Run to Cursor. This time the return is false because 0 ANDed with 1 is 0. step over the call to get bit for bit 7. Check all of the bit values. If you do the math, the values add up to 13. Stop the debugger. Add another function, from binary, that takes 8 bits and returns a uint 8t. This is another ugly bit of code that can be cleaned up later. For now, it works. The left shift assign shifts the value to the left by 1. The leftmost bit is lost, and the rightmost bit becomes 0. The value is then changed to add the bit value. Run the code so you can see the output of the whole program. You can step through the code to trace it if you wish. C does not specify how signed integers are implemented. A CPU could use 2's complement, 1's complement, or something else. The left shift and right shift operators are only defined to work on unsigned values. If you use the signed value, the program will likely behave differently depending on how the platform represents negative numbers. Using any bitwise operators, AND, OR, XOR, and complement with signed values is defined, but can still cause problems on some platforms. To be safe, it is best to only perform bitwise operations on unsigned types. The char type holds characters like A, B, and C. A char, like any variable, is a set of bits. C requires that a char be at least 8 bits. POSIX requires that a char be exactly 8 bits. C is less restrictive because it's designed to run as close to the CPU as possible, exposing parts of the underlying architecture. Different computers have different word sizes, which led to C making vague requirements, like a char is at least 8 bits. POSIX aims to be more portable, so it adds some additional restrictions, such as chars must be 8 bits. C's minimal requirements make binaries fast, but you do have to pay attention to the size of variables, which is why I encourage you to use the specific size ints unless otherwise required by an API. Many functions in C use char. C requires a basic execution character set, which consists of 91 characters. Lowercase a through z, uppercase a through z, 0 through 9, and a number of symbols. Any character not included in that list may not exist in a C implementation. POSIX requires the portable character set, which consists of 103 characters. The portable character set contains all of the characters in the basic execution character set, along with 12 additional characters. There are several character sets. The most common ones are ASCII and Unicode. ASCII is a 7-bit character set with 128 characters, valued from 0 to 127. ASCII has all of the characters of the portable character set, plus several non-printable control characters. Since a char is at least 8 bits, what about the characters between 128 and 255? These characters will differ depending on the language settings. Languages are specified via a locale. The installed operating system has a locale, each user can have a locale, and each process can have a locale. Locales can have different characters from one another. Every locale has the same first 128 characters and may have different characters beyond that. A char can represent 256 characters with values between 0 and 255. Some languages require more than 256 characters, meaning a char cannot represent them. Unicode defines over 140,000 characters for several different languages. Use the wchar type for Unicode characters. Handling Unicode characters is beyond the scope of this video. Remember that everything in a computer is represented with zeros and ones. A specific bit pattern represents a specific character. For instance, the uppercase A is represented by the number 65. 65 in binary is 01000001. Uppercase B is represented by the number 66, or 01000010. Lowercase a is 97. Create 3 chars. Give them values. Print them out as char, decimal, octal, and hex. All the values represent the same thing. These are just different ways of looking at the bits that make up the char. When you see the same line of code repeated, that's a good time to make a function. Make a function called printchar. Replace the printf calls with calls to the printchar function. You can also assign a char an integer value. You require a cast because going from an int to a char is a narrowing conversion. Int is 16 bits or more, and char is at least 8 bits. You have to tell the compiler that you know what you were doing. You can also assign a char to an int. Notice no cast is needed, as this is a widening conversion. Narrowing conversions lose bits, while widening ones do not. Regardless of the assigned values, you can still view them appropriately for their type. Remember that every variable has an address in memory. To print the address of a variable, use the %p conversion specifier. Declare another variable. The variables have different memory locations. On my machine, they differ by one number, which makes sense. My computer is byte addressable, and each char takes up 1 byte. The memory looks something like this. Assign x a value. Assign x to the y variable. The variables both have the same value. The memory address does not change, regardless of changes to their values. Notice that memory addresses probably change each time the program runs. This is expected and is a detail of the underlying operating system. Now the memory looks something like this. However, if you change the value of one of them, the other does not change because they are independent memory locations. A pointer is an essential type in C. Use the asterisk to declare a pointer variable. Z has a memory address, just like any other variable. The value of a pointer is a memory address. Use the address of operator, ampersand, to assign Z the address of X. The value of Z is the address of X. If you dereference the pointer with asterisks, the value at the memory address is used. If you change X, then it changes for Z as well. When the dereferenced value Z is changed, it changes X. There's no difference between pointer Z and X. They are the same thing. Pointers allow you to access the memory address of another variable, which means you can use multiple variables to change a value. C makes heavy use of pointers, so you must have a good understanding of how they work. Some compilers can warn about type mismatches between the conversion specifier and the variable passed in. The compiler now complains that char pointer pointer is not a void pointer. %p requires a void pointer. Casting the variables to void pointer fixed the warnings. An array is simply a contiguous area of memory. An array has a length, which is a number of elements it can hold. However, unlike some languages, C has no built-in mechanism to remember the length of an array. To declare an array, give it a name and a size. Word is an array of 5 characters. 0 is the index of the first element of the array. The valid indexes are 0, 1, 2, 3, and 4. Each index has a unique memory address. Depending on the platform, the memory might have a value of 0 or a random value. Do not depend on that behavior, as another compiler or operating system may behave differently. Print out the address of the array and each element. Notice that word and word0 have the same address. The address of an array is the address of the first element of the array. Another way of looking at it is that the array variable is a pointer to the first element of the array. Set the word to hello, character by character. Print out each element of the array as a character. Make another array for world. A string is an array of characters. Printf can print out strings, so pass the word variable to printf. Depending on your platform, you will see something odd happened. Hello also printed out world. Remember that memory can be seen as a large array. Nothing prevents you from accessing memory past the end of an array. The %s conversion specifier works with strings, not arrays. But a string is an array, isn't it? Almost. A string is an array that ends with a null byte. You must remember to add room at the end of the array for the null byte. If you don't, printf will just keep going past the end of the array until it finds a byte with the value of 0. Update the code to make room for the null byte at the end of each word. You can change the word at index 8, which will alter the memory for word 2, changing the string world to something else. You must be careful to only access the memory that belongs to the array. C won't prevent you from accessing the wrong values, which can result in random, strange behavior that is hard to track down. The compiler flags you have used so far are the minimum you should use. Other compiler flags will help you find more problems, such as accessing past the end of an array. A compiler can issue two basic types of warnings: compile time and runtime. Compile time warnings are checked based on the source code. Runtime warnings are problems found while the program is running. There are a lot of flags. When the cmakelists.txt file changes, be sure to reload it. Rather than list them all here, look at the video's description to find the current set of flags that I recommend. The recommended flags may change over time, so you may want to check for changes periodically. You can also add or remove flags to suit your needs. Before you remove a flag, you should understand the ramifications. The description also includes a link to the GCC documentation for the flags. With these flags in place, the compiler warns about accessing the word variable at index 8. It's best to find a bug at compile time. If you can't find a bug at compile time, it's best that the process crashes and tells you what went wrong. Run the program. It finished with an exit code of 1. Remember that 0 indicates success and any other value means the program failed. The program crashed and reported the line that the error occurred on. Select the Sanitizers tab. There is a problem on line 23 of main.c. The problem is that the word variable was accessed outside of its valid bounds. It's excellent that the problem was found at runtime, but it's better to discover the problem before running the code. Change the compiler to CLion. Rebuild the program. Both the GCC and CLion compilers warn you about the problem. You didn't need to run the program to find and fix the problem. Pay attention to the compiler warning messages to save yourself a lot of time and headaches. You can switch between GCC and CLion whenever you want. Using more than one compiler and all these flags helps eliminate bugs from your code. You should install another distribution and run your code on it to help ensure there are no other problems to find. It's essential to keep your code compiling clean and test it often to find problems. The longer you wait to fix things, the harder it will be. Valgrind is a suite of tools that can find many types of runtime errors. One of the most important tools is memcheck. GCC and CLion can perform runtime checks, such as finding out-of-bounds issues with arrays, but they can't check many other things. Memcheck can't check for local arrays going out of bounds, but it does detect many other kinds of memory errors. Just like compiler warnings, lint, and runtime compiler checks, it's essential to run memcheck on your code while developing it. If you wait for things to go wrong in your code before you maybe start paying attention to the tools, you'll be wasting a lot of time. You can run Valgrind on the command line. You may need to install Valgrind. It probably doesn't work due to some ASAN runtime error. As with most tools, you can run it on the command line or within the IDE. Run memcheck. It doesn't work because of the compiler memory sanitizer checks. Tools like the compiler and Valgrind instrument the code, which means they put additional instructions into the binary, and sometimes the instructions for one tool interfere with another. Comment out the sanitizer flags for now. Run memcheck. Click on the Valgrind tab. There are no memory issues found with this code. Remember that the compiler can find things that Valgrind can't, and vice versa. Remember that the stack memory is not initialized to 0 on all platforms. Print out the array elements before assigning hello and world. Rerun memcheck. There are 11 warnings. The call to printf seems to be the issue. It isn't safe to use a variable that has not been initialized. Sometimes the compiler can warn about uninitialized variables being used, but it's hard to warn about array elements. Before deleting the calls to printf, run memcheck on the command line. You get the same information, but it's not as easy to deal with. In the IDE, you can just click on the warning, which will take you to the line of code. It's inconvenient to comment and uncomment the compiler flags when you switch between compiler checks and memcheck. Add a variable for the sanitizer. If the sanitize variable is true, add the flags to the compiler. Now you can change the one variable to swap between compiler checks and memcheck. As I said, the fancy IDEs make using the command line tools easier. It's still important to know how to use these tools on the command line because sometimes an IDE isn't available or the IDE doesn't expose all the features that the command line does. It may seem like I'm harping on these tools, and I am. If you want to be an effective developer, use all the tools you can. Take the time to learn how they work and what the messages mean. Use the tools consistently from early on in the development process, fix any issues as soon as they are found, and run the tools often. You can do a few things to make CLion more streamlined. For this part, you can go through the settings and make any changes you wish, or leave the defaults. If you want to use my settings, you can import the ones found in the link in the video description. First, change the cmakelist.txt template to match the template I have provided you. Go to Settings, Editor, File and Code Templates, Other, CMake, C Projects, cmakelist.txt for C executable. Paste the template I have provided. Check the video description for a link to the current template. Create a new project. You have to make the source and include directories and move the main.c file into the source directory by hand. Once the project is set up, you should just need to keep the source and header variables up to date. Head back to the settings. Live templates are basically editor macros. You can start by typing something, such as for, and when you press the tab key, the basic outline of a for loop is created for you. You can add live templates in Settings, Editor, Live Templates. Add live template. Call it up, short for unused parameter. Add the code to the template. Set it for the declaration context. Go to the main function. Type up and then press the tab key. You just have to move the pop line after the function. You can change the font in the editor if you want. Inspections are lint warnings that the IDE will show in the editor. You should not use a tab character to indent. Different developers can set their tab stops differently. A mix of tabs and spaces can make the code inconsistent and hard to follow. Most editors will convert the tab key to spaces, which is fine. The code style has a lot of flexibility. You can choose your brace placement, It's worth looking at the other settings to see what else you may want to configure. One final setting is plugins. Plugins add features to the IDE. You can even develop new plugins yourself. Functions can take parameters and return values. A stack frame is the memory area used to hold the parameters and local variables. Add a variable to the main function. The compiler creates a stack frame for the main function with enough room to hold a char. CLion tidy has a few complaints, including the name C is too short. Generally speaking, you should give variables descriptive names. The naming quality is less critical if a function has a single purpose, few parameters, and is small in size. Add a flag to the cmakelist.txt to turn off the warning. The compiler warns about the unused variable. Disable the clang warning to reduce the noise. Depending on how the cmakelist.txt file that you're using is configured, you may not see these warnings. Until the variable is assigned, the value at the memory location is random. There may be some additional warnings to disable in CLion tidy. The warnings can be disabled because the compiler also warns about them. Make a new pair of files, display.c and display.h. Add them to the cmakelist.txt file. Add a new function, display, that takes a char. Print the address of C in the display function. Print the address of C in the main function. Call the display function. The memory addresses are different from one another. The display function gets the stack frame large enough to hold the parameter. All variables in C are passed by value. Passed by value means that a copy of the argument is made and pushed onto the stack. change the value of c inside the display function. The value of c in the main function is unchanged. The main function is called the caller. The display function is called the callee. Changes to a parameter in the callee are not reflected in the caller because a copy of the parameter is passed in. Notice that the memory is not cleaned up when the function returns. At some point, another function will be called and use that memory for its stack frame. That function will have seemingly random values, the leftover values from previous stack frames. Parameters are conceptually broken down into three categories: in, out, and in-out. A function can only use the value of an in parameter. A function only sets the value of an out parameter. A function can use and set the value of an in-out parameter. Out and in-out parameters must be pointers. Remember that C uses pass by value, meaning a copy of the argument is made. Any changes made inside the function are made to the copy. Pointer arguments are still passed by value. However, just like pointers within a function, a parameter can change the value of the argument it points to. The display_to function is the same as display, except it uses a pointer for the parameter. The C parameter has been used as an in-out parameter. You should document the use of parameters. The @param tag can take in, out, and in-out directions that indicate how the pointer parameter is used. Another reason to use a pointer is if the variable to be passed in is large. Remember that arguments are passed on the stack. A large value will take up a lot of space on the stack. Pushing values onto the stack slows the program down and uses more memory. Arrays are passed as pointers of the first element to avoid having to push each element onto the stack. Since an array is a contiguous area of memory, you can go from the first element to the last with just the pointer. The operating system calls the main function when the program runs. As a function, main can take arguments. The main function typically gets its arguments from the command line. For example, when you type gcc-standard equals C17, the -standard equals C17 becomes an argument to main. A program can take 0 or more arguments. The main function has two parameters, argc and argv. Argc, or argument count, is the number of arguments in argv. Argv, or argument vector, is a null-terminated array of pointers to strings. Remember that a string is an array of characters that ends with a null byte. Set a breakpoint. Run the program in the debugger. Argc has a value of 1, even though no arguments were passed to the program. argv0 is the path to the binary. Every C program can find the program's name by looking at argv0. This value isn't commonly used, but it's there if needed. Stop the debugger. Edit the configuration. Pass in Hello World as a program argument. Be sure to surround it with quotation marks. Rerun the debugger. argc has a value of 2. You can't see argv1. Add a new watch for argv1. Look at the memory view for argv0. On my platform, the program's name ends with a null byte, followed by Hello World. Use argv1 in printf. It prints out the message passed into it. You have written an elementary version of the Unix echo utility. What happens if you don't pass in any arguments? On my machine, it crashes. You might get something different. For example, it may print out null. Run the program with memory sanitizers turned on. Depending on your platform, it may or may not find an issue. Run memcheck. It also finds an issue for me. Again, your platform may have no issues found. These implementation differences are why it's essential to test on multiple platforms. The argv array is null terminated. That means that argv is 1 larger than argc reports. If no parameters are passed to the program, the valid indexes for argv are 0 and 1. 0 is the program's name, and 1 is the null terminator. Even with all the tools at your disposal, you still need to understand what is happening and realize that the tools won't find everything. The compiler can find syntax and semantic issues. The runtime can find some memory issues. Valgrind can find other memory issues. These tools can find many issues, but not all. In addition, only a human can find logic issues. Fortunately, the compiler did help you find the issue, sort of. Rebuild the program. There's a warning that argc is unused. The most important part of this section isn't how command line arguments work. it is that you always need to run the compiler before you run the program in an IDE. On the command line, you have to compile and then run. The IDE makes it easier by compiling when you run. However, this makes it easy to skip over the compiler warnings. Don't skip compiler warnings. Deal with them as soon as you can. You can silence some warnings with pragmas if you need to, but only if you really understand that the warning is safe to ignore. There are many things you can find out about a character. For example, is it uppercase, lowercase, alphabetic, or a digit? The ctype.h header file has several functions related to character classification. Notice that the functions take an int instead of a char. For reasons explained later in another video, C has several APIs that use int to represent a character. Just remember that each char is a specific pattern of bits. An int can have the same bit pattern, just with leading zeros. When C treats int as a char, it only looks at the low-order bits, ignoring the leading zeros. The is functions return 0 if the char is not of that type, and non-zero otherwise. For example, isAlpha returns 0 for 5, and non-zero for A. ToUpper and ToLower change the case of an alphabetic character. For example, ToLower A returns lowercase a. If a character is not alphabetic, then the character passed in is returned. The POSIX specification says, upon successful completion, ToUpper shall return the uppercase letter corresponding to the argument passed. Otherwise, they shall return the argument unchanged. This sort of formal language is something you need to get used to when dealing with formal specifications. You need to pay careful attention to words like can, may, must, shall, will, could, might, and should, and treat a specification like a legal contract. Write a function called display that prints out all the attributes of its parameter. check the results and notice that some of the values are strange. 0 is false and non-zero is true. The specification didn't mandate the values for true, so an implementation is free to return any non-zero value. A different implementation could have all the functions return 0 or 1. It is essential to code to the specification, not what a particular implementation happens to use. So do not check for a particular value, just check for 0 and non-zero. A loop is a way to execute instructions repeatedly. There are many different loops, but they all boil down to executing some code as long as a condition is true. The code inside of a loop is called a block. C starts a block with an open curly brace and ends a block with a closed curly brace. Functions also use blocks. A block is a convenient way to group code. The most commonly used loop is probably the for loop. A for loop has 4 different parts: initialization, condition, body, and post. Viewed as a flowchart, a for loop looks like this. The initialization happens once. The condition is checked. If the condition is true, the body executes. After the body executes, the post step runs. The condition is rechecked. If it is true, the body executes again. If it is false, the loop ends. Each part is optional. You can just stop the program if you make a loop that never exits. Press Ctrl-C to kill a process running in the terminal. Write a program that takes an argument from the command line, argv1, and prints out each character as an uppercase letter. Pause the video, write the code, and then resume the video to see my solution. There are a few ways to code this, but the most practical way is to loop until the null character is reached. The string can be accessed as an array using indexes. The string can also be accessed as a pointer, dereferencing each character. Realistically, the compiler should generate the same code for both. My preference is to pick whichever is clearer or the more obvious way. If there is a significant difference in the speed of the two, you can deal with that later. It is more important to get the correct result slowly than to get the wrong result quickly. In general, use a for loop when there is a bound. For example, going from 0 to 10. Use a while loop when the terminating condition is unknown, such as when a user needs to type done to end the loop. The difference between the two cases is subtle. A for loop is typically used when the programmer knows when the loop will end, and a while loop is usually used when the user or some other external entity controls when the loop will end. A while loop has 2 parts: condition and body. Since the while loop lacks the initialization and post steps, you must do them for yourself. First, the condition is checked. If it is true, the body executes. If it is false, the loop ends. A while loop where the programmer has provided the initialization and post steps looks like this. Notice that it's the same as the for loop. The code looks similar to a for loop, just a bit more spread out. For loops and while loops both check the condition before performing the body. It can lead to hard-to-follow logic when you want to ensure that the body happens at least once. It is easy to convert a while loop to a do-while loop. The problem with using a do-while loop with this code is that it will fail if argv1, 0 is the null character. Do-while is guaranteed to run at least once compared to for and while, which are not guaranteed to run at all. Consider a while loop that asks the user for a number between 1 and 5, but the user keeps entering 6. This code uses pseudocode rather than actual code. Pseudocode is a close-to-English explanation of what the code needs to do. Pseudocode lets you think about what needs to be programmed before it is coded. You can often start a function by commenting the pseudocode of what it's supposed to do, and then replace the pseudocode with real code bit by bit. A do-while loop makes this much easier because a condition is checked after the body. Use the best kind of loop for the task you were doing. Loops are part of a broader topic of control. Conditionals are types of control that allow a program to make decisions. A loop is a conditional that does something while a condition is true. Once the condition is false, something else happens. An example of a loop is going through the characters of a string until the null byte is seen. Not all controls are loops. Any construct that causes a program to move to something other than the next line is a form of control. The if statement is a fundamental way to perform branching. Branching means the code can take one or more paths based on a set of conditions. If statements in C all use Boolean values. However, it's not that straightforward. In C, when dealing with conditions, 0 means false and any other value means true. Various things mean 0. The integer 0, the null byte, and the null constant. Essentially, any integral value that has all the bits set to 0. Null is used for pointers to indicate that they are currently pointing to nothing. The braces are optional for an if statement, but I strongly recommend you put them in, even if an if statement only has one line. Later on, there's a good chance that you'll have to add in another line, which means you'll have to add the braces. And any time you alter code, you can break it. Adding the braces makes the code easier to read and saves you from adding them later, reducing your chances of making a mistake. You can put the braces wherever you want. I choose to put them on a line by themselves. My rationale is that it's easier to line up the braces visually. Place the braces wherever they make you happy or where your job requires them. A return statement leaves the current function. Generally speaking, a function should only have one return statement at the very end of the function. A common mistake that new programmers often make is to have a return statement in an if statement, followed by an else statement with a return. No more code executes when a function returns, so the else is not needed. A better idea is to create a temporary variable. Set it in the if-else, and then return. It's okay to violate the one return to exit early if a precondition fails. A precondition is something that must be true. For example, there's no point in running the loops if the string is pointing to null. You can return at the end of a void function, but it's unnecessary. Sometimes you may want to skip over an iteration of a loop. To do that, use a continue statement. Write a function that prints out every other character of a string. When the number is odd, the rest of the body is skipped. The continue works for this, but there's a more obvious way to do it. Nothing says that you have to increment by 1. You can use plus equals to increment by any value that you want, such as 2. However, there's a bug with using plus equals 2 in this case. It skips past the null byte, so the loop does not stop where it should. Always try to write the simplest and most obvious code to get the functionality required. Tricky code is hard to follow, especially at 2 a.m. when you're tired and frustrated. Tricky code is also harder for others to understand. Code is read more than it's written. There's a saying that the code was hard to write, so it should be hard to read. Don't follow that saying. A better saying is don't comment bad code, rewrite it. Any code that's hard to understand can be considered bad. Sometimes it makes sense to stop a loop before it ends. Write a loop that prints out the characters until a digit is seen. quickly test the code to make sure that all the characters are printed. Add a flag variable. If the character is a digit, set the flag variable to true. If the flag is not set, print out the character. End the loop when the null character is seen, or the flag is no longer false. Test the code. Rather than explicitly compare to true or false, you can just use the variable name for true and not variable name for false. Make sure the code still works. The flag variable makes the code hard to follow. The break statement exits out of the current loop. Remove all the uses of the flag and break out of the loop instead. The code is now much easier to follow. When a number is found, exit the loop. If-else statements can become quite long. Write a function that converts a single digit to a word. The digit 1 becomes a word 1, and the digit 2 becomes a word 2, etc. Pause the video and write the function before looking at my solution. Using if-else is pretty verbose. Write a loop to test all of the digits. A for loop can start at any number, not just 0. Remember that characters are numbers too. Start at 0 and go to 9. Rather than print out the result multiple times, it's better to use a temporary variable. Don't forget to handle when the character is not a digit. A switch statement can be better in this case. It isn't smaller, but it's easier to follow. The code runs straight through if you forget to add the break statement. This is a common bug. Notice the compiler and the lint tools warned about the issue. The const qualifier warning will be covered later on. A special case, default, handles any values not in the case statements. Default is basically the same as an else statement. A CPU may have some sort of lookup table instructions that the compiler can use to make this code faster than the if-else structure. A compiler could, in some cases, convert the if-else structure to use a lookup table instruction, but that is compiler specific. You should generally not write code because of what you believe the compiler may do. Write the code to be clear and trust that the compiler will do a good job. If you find out later that the code is slow, you can speed it up if needed. It is more important to write simple, straightforward code than fast code. The odds are that the compiler will have an easier time optimizing the simple, straightforward code than it will something that you do in the name of speed. A function is another way to transfer control to something other than the next line of code. When a function call is made, the instruction pointer changes to the memory address of the function's first instruction. Functions can be assigned to variables as well. A variable holds the address to the first instruction of the function, which makes the variable a pointer to a function, usually called a function pointer. A function pointer has a slightly odd syntax. Convert is a pointer to a function that takes a char pointer and returns void. Create two functions that have the appropriate signatures. If an argument is passed to the program, assign the variable stirLower. Otherwise, assign the variable stirUpper. Don't use the parentheses when you do the assignment. That will call the function instead of getting the address. Write the stirUpper and stirLower functions. To call the function, just use the variable name. The call is the same as if the function name had been used. Remember, a function call is just the instruction pointer changing to the address of the function's first instruction. The CPU does not know the difference between direct and indirect calls. You should run the program with and without arguments to test it. Pay attention and don't make simple copy-paste mistakes. You can also pass function pointers as arguments to functions. You can pass null to indicate that the function should not be called. The program crashes. Check the sanitizers and memcheck to see if they can tell you why. Null is not a valid address for an instruction, so the program crashed. If the parameter is not null, then call the function. Looking only at the perform function, it's impossible to tell what the code does. The function doesn't know if it makes the string uppercase, lowercase, or something else. You can also add new functions and pass them in without modifying this function. This generic function provides an algorithm, but the function's behavior is left up to the programmer that calls it. All it knows is that the function does something to the string, and then the possibly modified string is printed out. Write a program that converts argv1 to uppercase if -u is given and lowercase if -l is given. If neither is given, print out the argument unchanged. There are many compiler warnings. For now, we will ignore them because we will fix these issues later in the video. Pass in an argument. Try some valid and invalid flags to see what the results are. There is a bug. Set a breakpoint and run the debugger. A small typo can ruin your whole day. The debugger is invaluable when you want to see what's happening in the program. Do some more testing. The basics are in place. It's time to add the actual functionality. Test the new code. Run memcheck to see what's wrong. Null again. Rather than test for null, add a new function, null converter, that just prints out the argument. Test again. Everything seems to work. Command line option parsing can be tedious. There are two kinds of arguments, positional and named. A positional argument is at a specific position. The position can be absolute or relative, such as the first argument, the last argument, or the third argument. In POSIX, named arguments, or flags, are passed with a switch. A switch consists of a dash followed by a single character. ls-la tells the ls command to perform a long listing of all the file system entries in the directory. Switches can be combined, for example, ls-al or ls-la. Switches can also take arguments. nl-ba tells the nl command to use the body numbering style A, which means to number all lines. POSIX provides the getopt function, which makes it easier to create programs that take arguments. The GNU library also provides the getopt long function, which is not as portable, but realistically, it should exist for all POSIX systems. Getopt long allows for the use of single-character or multi-character switches. For example, if GCC were implemented using getopt instead of getopt long, -standard C17 would likely be -s C17. If you wish to write portable programs, use getopt. If you're okay with the possibility that a program may not run on some obscure platform, you can use getopt long. The GNU library is open source, so if you find yourself on a platform that does not support getopt long, you can always port it over. For now, we will just use the POSIX getopt function. Remove the previous option parsing code. The purpose of getopt is to simplify the handling of command line arguments. The handling will still be tedious, but it will be far easier than doing it yourself. Typically, getopt is called in a loop. Pass getopt to argc, argv, and the op string. The op string tells getopt the name of all the options and if they take arguments. Use colon to indicate that the option has an argument. Getopt returns each flag it finds in argv in the order that the user passed them on the command line. The argument in the current flag is available in the opt-arg variable. If the user forgets to pass an argument to a flag that requires one, getopt returns the colon character. If the user passes an unknown argument, the question mark is returned. The default should be impossible to get to. Assert causes a program to crash when it's compiled in debug mode, which is fine for something that should be impossible to happen. If neither U or L was passed in, then set the converter function to the null converter. The other string conversion functions have names that start with stir. Let's be consistent with the naming. Change the name of null converter to stir none. Set the message to null so you can tell that it has not been set yet. The message will be there if the user passes in enough arguments. Getopt requires that all flags appear before other arguments. The opt index or option index is set for each non-flag argument. If the message is still null, complain. Run the program with no arguments. Run it with a message. Crash. Why? I did not compile it before running and had a simple typo. Rerun the program. Run it with the U and L flags. It seems to work. Compiling the code before running the program is good, but it only helps if you fix the warnings. Ignoring the warnings has caused a few problems now. The more warnings you have to sift through, the easier it is to miss something important that could save you valuable time. You could turn the warnings off, but then you would have no help from the compiler. The better thing to do is to stop and fix the code to remove the warnings. When you do this, you may find that some hard-to-fix bugs simply vanish. Some fixes may cause something to crash instead of continuing with the wrong result. Anything you can do to remove bugs or make them easy to find is helpful. The includes being not in alphabetical order is trivial to fix. Sorting the includes alphabetically doesn't hurt, and it can make it easier to find things that you have included. Getopt returns an int, not a char. A char is smaller than an int, so important information could be lost. Multi-threading is beyond the scope of this review, but it is an important warning. This code is okay to have such a warning, but you should silence it. Rather than use a pragma, clang tidy uses special comments to silence warnings. Const will be covered later. For now, change the variable to const. Exit is also not multi-threading safe. The case is missing a break. Now the code compiles cleanly. Any new warnings will be easy to spot. Fix the warnings as soon as you see them. Do not let them mount up. A test plan helps you do a complete job of ensuring that all possible outcomes, good and bad, are working. Each test can be a success or a failure. The program should fail when no message is provided, both the U and L flags are passed simultaneously, or an unknown flag is passed. The test plan documents the expected results when a test is successful. The test plan ensures that everyone knows how the program should behave in every condition. The first thing you should do when creating a program is to devise a test plan. Starting with the test plan gets you focused on what the program needs to do, how it should behave, and what error cases to consider. For example, what happens when the user simultaneously passes -u and -l? Do you make it an error? Do you take the first one past? Do you take the last one past? Thinking about these cases up front saves time. Rather than discover the issue when you think you're done programming, you've considered it right up front before anything was designed or coded. Just like finding a bug at compile time is better than runtime, it is better to find design issues before you start programming. You can choose to handle the error conditions first or last, or you can choose to do things in any order you please. There's no right or wrong way to approach the testing. Here we will start with the tests that are not errors. Now try the program with no message. The failed test is marked in green even though it failed. The test was correct, the expected outcome was a failure, so that means that the test passed. How about -u with no message? What about -l with no message? What about an unknown flag such as -x? And finally, passing -u and -l simultaneously. All of the tests work as expected. Currently, the memory looks like this for main. As the arguments are processed, the memory is updated. A struct groups related variables. Structs are a convenient way to pass multiple arguments at once. Create a struct for the options. The options consist of the message to print and a pointer to a function to convert the message. Move the message and convert variables to the struct. Make a function to initialize the members of the struct. Generally, a struct should be passed to a function as a pointer. If you do not pass it as a pointer, a copy of the struct is made on the stack, which is expensive. Remember that a function has to push all of the parameters onto the stack, which takes time and memory. Update the code to use the struct members. Test that the program still works. The main function is a bit large and is doing too many things. You can move the getopt functionality to a function. Highlight the code to move, right mouse click and select Refactor, Extract Method. Change the function name to parse arguments. The variable is not needed in the main function, so do not pass it as a parameter. Move the C variable from the main function to the parse arguments function. CLion has made a new function from the highlighted code. The code was replaced with a call to the new function. CLion writes the code differently than I would, but both ways work equally well. Looking at the memory now is slightly different. A column has been added for the struct fields. You should be noticing a pattern. An array variable is a reference to the first element of the array. A function pointer is a reference to the address of its first instruction. A struct variable is the address of its first field. Each of these items represents an area of memory, and the variable refers to the first element of that memory. You can use the debugger to trace the execution, or do it by hand on paper. Let's see what happens when the program is run with the arguments -u and high. The main function calls the initOptions function, passing the address of the option struct variable. First, the convert function field is set to null. Then the message field is set to null. Notice that there's only one copy of the option struct, and the initOptions function accesses it through the parameter passed in. When the function returns, the stack frame disappears, but the memory values are left. Remember that sometimes C has random values for variables. These random values are simply the leftover values from previous stack frames. The parseArguments function is called. The stack frame consists of the parameters to the parseArguments function and the C variable. The getopt function assigns U to the C variable. That sets the convert function in the options to the address of the first instruction of the stirupper function. The message field is set to whatever argv2 is in memory. The function returns control to the main function. The stack still has the values from the parseArguments function variables. The convert function pointer is called, passing in the message field. The convert function pointer is pointing at the stirupper function, so that is the one that gets called. The message parameter had its value pushed on the stack when the main function called the stirupper function. The I and converted variables do not yet have a value assigned to them, so they have the value of whatever happened to be in memory from the previous stack frame. The for loop starts and initializes I to 0. The toUpper function is called, passing in h. The toUpper function returns h, which is assigned to the converted variable. Printf is called. The %c string has an address somewhere in memory. The arguments to printf are tricky. This is a simplified representation of them. Printf causes the h to be displayed on the terminal. Printf returns, and the for loop continues, incrementing I to 1. toUpper is called with the I character. Uppercase I is returned and assigned to the converted variable. The converted variable is passed into printf, which displays it to the terminal. Printf with /n to end the line is passed in. Likely, the compiler optimized this call to be the putS function instead of printf. The loop finished as the next character was in the null byte. The function returns, and the main function returns control to the shell. The operating system ends the process. The operating system can allocate the memory that this process used to another process later. For security reasons, an operating system may zero out the memory before another process uses the memory. Alternatives to zeroing out the memory would be to set it to random values or to leave it unmodified. If the memory is left unmodified, things like passwords stored in the memory will be recoverable when the memory is allocated to another process. The scope of a variable or function dictates what can use it. In general, the scope should be kept as small as possible to avoid mistakes. A stack frame is one form of scope. Tools such as the memory sanitizer checks and memcheck can detect when the stack frame scope is violated. Most scopes are enforced by the compiler or linker. By default, all functions are in the global scope. Any function in any file can call a global function. Variables not declared inside of a function, struct, or union are at the global scope. Making global variables is generally a bad idea, but sometimes they are necessary. The variables used by getopt are global. When the unistandard.h header file is included, the global variables are made available to the compilation unit. You can right-mouse click on a variable and select Go to Declaration or Usages to be taken to where the variable is declared. On my system, it is not in the unistandard.h header file. The getopt core.h header file will ultimately be included in the unistandard.h header file. Implementations are free to do things however they wish, as long as the general requirements are followed. When unistandard.h is included, these functions, types, and global variables are made available. Local scope is confined to a function. Any variable declared in a function can only be seen within that function. If another function tries to access it, the compiler will issue an error message saying that no such variable exists. The local scope includes all the function parameters and variables declared inside the function. The block scope is any variable declared between the open and closed curly braces. If, else, case, for, well, and do all support blocks. Any variables declared inside of a block are visible only within that block. As with local scope, if a variable is accessed outside of its block, the compiler issues an error that the variable cannot be found. The variables declared in the for initialization are also scoped to the for loop. Try to give variables the smallest scope possible. Start by assuming the variable can only be used within the current block. If the variable needs a broader scope, move it up a block. The smaller the scope of a variable, the less chance there is to make a mistake with it. Now is a good time to separate the string functions from the main program. The functions inside of a compilation unit should be related to one another in terms of functionality. Make a file called strings.c and the associated header file. Move the strings.h header file to the include directory. Add the .c and .h files to the cmakelists.txt file. Move the function prototypes to the header file. Move the functions to the C file. Include the header file in the main.c file. Make sure that the code compiles cleanly. Test the program to make sure that it still works. Declaring functions and variables as static forces the compiler and linker to ensure that they can only be used in the compilation unit they were declared in. It is a good practice to declare any file-level functions or variables as static. It is important to ensure that non-static global variables are declared only in one file. If a non-static function or global variable is defined in 2 or more compilation units, the linker will give an error that there is a duplicate symbol. The opposite of static is extern, short for external. Extern tells the compiler that the variable is declared in another file, but this is the name and the type of the variable. The opt-in variable is declared as extern in the header file. Some file in the C runtime library, probably getopt core.c for my system, will contain the actual declaration of opt-in. Global variables should be used sparingly, but when they are used, make sure that you declare them properly, or your code will likely not compile. The string.h header file contains several function prototypes to make it easier to work with strings. The 4 functions you're most likely to use are strlen, strcomp, strcopy, and strcat. Strlen counts the number of characters before the null byte. Strcomp compares 2 strings. Strcomp returns 0 if they are the same and non-zero if they are different. This is one of the few places where 0 means true in C. 0 does not really mean true though. It essentially means that there are 0 differences between the strings. You cannot infer any meaning from the actual non-zero number, except that greater than 0 means the first string was alphabetically greater than the second string, and less than 0 means that the first string was alphabetically less than the second string. Strcopy copies one string to another, including the null byte. It is up to you to ensure that the destination variable has enough memory to store the string. A common mistake is to forget to account for the trailing null byte in the size of the destination string. Strcat appends a string to the end of another string. The appended string overwrites the current null byte at the end of the destination string. Strcat ensures that the destination string ends with a null byte. It is up to you to ensure that the destination variable has enough memory to store the appended characters. Many of the functions in the string.h header file declare their parameters as const. Const means that the variable will not be changed. Const char pointer means that the function will not modify the characters in the string. A const struct pointer means that the function will not modify the struct members. Any const value means that the function will not modify the variable. Strcopy is an excellent example of using const. The destination string cannot be const because it will be appended to. The source string should be const because strcopy must not modify it. Using const properly removes the possibility of many bugs in your code. Any time that a function is meant to only read a pointer, not modify it, the parameter should be declared as const. What happens if you do try to modify a const pointer? The compiler will issue a warning or an error. If you ignore the warning and run the program, it may crash because the compiler may allocate the variable in read-only memory. When a process attempts to modify read-only memory, the platform causes it to crash. You can view memory as something like this. There are two areas, the stack and the heap. The stack is where local variables go. The heap is where the compiler stores global variables, including constant strings. Depending on the platform, some of the heap may be read-only. The rest of the heap is used for dynamically allocated memory. Dynamically allocated memory is memory that can live longer than a function call. Stack variables are only accessible within their stack frame. Dynamically allocated memory is accessible as long as it remains allocated. Until now, the stir-upper, stir-lower, and stir-none functions have printed out the modified value. What happens if you want to convert a string, but not display it? Change the function to modify the string instead of printing it. Print out the modified message. Depending on your platform, this may or may not work. Let's force the issue and convert a hard-coded string. This crashes for me. Why? My platform allocates the string in read-only memory, and the stir-upper function tried to modify it. To fix this, the function must return a new string the same size as the string passed in. The modifications take place in the newly allocated string. Update the prototypes and fix whatever code breaks. Make the passed-in string const because the functions must not modify them. You need to create a new string large enough to hold the characters of the string that was passed in. You cannot hardcode the size because every string passed in could be different. The strlen function returns the number of characters in the string, excluding the null byte. The malloc function dynamically allocates memory from the heap. Malloc takes the number of bytes to be allocated. Make sure you add room for the null byte when you allocate the memory. Use strcopy to copy the string over. Strcopy will copy the null byte too. Make a variable to store the returned string. Print out the now modified string. Run the program. It worked. Run the program through memcheck. The memory has been lost. Freeing dynamically allocated memory when it is no longer needed is essential. If you do not free the memory, you run the risk of running out of heap space. At the very least, your program will probably use more memory than needed. Instead of finding the string length and using malloc, use the strdup function. Strdup does the strlen, malloc, and strcopy for you. Avoid having functions print things out. You don't know what a programmer will want to do with the value. Perhaps he will write a GUI program and the printf will not be seen. Perhaps he'll write a console program and do not want the value printed out because they are using it internally. Now that the filter functions are clear, it is time to document them. Be sure to say that the memory must be freed. Other programmers need to know when something is dynamically allocated and if they are responsible for freeing it.